All right, here we are in 7.2. We're looking at sectors of circles, both arc length and area. This diagram in here in yellow, that's a sector. Think of it like I don't know, circle's a pizza and a sector is like a slice of pizza. It's like a chunk of a circle. Both sides that form it are radii. I believe radii is plural for radius. And this part over here around the edge, that's called an arc or an arc length. We've used S to represent it. So we're looking at how we take this angle here, and that's what this section is about, is the length, well, both of these things. The length of the arc and the area of the sector are determined by how big the angle is. Okay, that's not a mind-blowing concept. Here's another sketch of a circle. The angle I drew in is bigger than the one in this first diagram. And as a result, the intercepted arc is bigger and the area is bigger. Okay? But there are relationships, particular relationships between the angle and the area and the arc length. Let's look at arc length first. Okay? Here's the formula if we're in degrees. And I'll show you why here in a minute, that we have to have two formulas for each unit of measure. Think about it like this. Arc length, if we thought of it all the way around the whole circle, we have a name for that. It's called circumference. It's probably a term that you've heard before. Think about circumference as the arc length of the whole circle, or a 360-degree angle. So what we do here is maybe a better way to think about this formula is we take the angle over 360. Okay? And so we kind of look at what proportion of a circle are we dealing with. For example, if theta was 90 degrees, we'd have 1/4 of a circle. Well, that's what this component is really about, is what's the proportion. Then we multiply it by the entire circumference. So if the angle was 90 degrees, we want 1/4 of the whole circumference. Okay? Now the proportions can get more complicated than that, but that's the idea. Here's the proportion. There's the circumference. Okay? Now, the only thing that's going to change in radians is theta is going to be over 2 pi. I'm still going to multiply it by the circumference. Okay? Well, as I kind of work this one through, look what happens here when I have theta times 2 pi r over 2 pi. Those cancel, and there we go. An even more simple formula. The arc length is just the radius times theta. And this is, again, if the angle is in radians. So radians actually works a little bit better for calculating arc length than degrees do. But the idea is the same. What proportion of the circle times the circumference? Okay, bottom line, these are the two formulas you need to know. Okay, I will do some examples with these in a minute, and this stuff isn't super relevant for what you'd see on a test. I'm just trying to give you a little background info so that these formulas, make sense. I always think we're better inclined to use the formulas more effectively if we take a little time to look at the fact that these formulas make sense. They're not just random numbers and variables all slammed together. There's a rhyme and a reason to them, and it's good to look at that. Let's go to area. It's the exact same concept over here. Theta over 360, we can think about it that way, times, now instead of circumference, I want that proportion that I'm looking at based on the angle relative to pi times radius squared. That might be a formula that looks familiar. That's area of a circle. So again, there's this component with the proportion of the circle I'm looking at relative to the whole. It's just that right here I'm looking at it relative to area, whereas with arc length it was relative to circumference. Okay? With radians, again, we see the same thing happen here, that this is still relative to pi times radius squared. But once again, I have to think about the angle relative to 2 pi, because that's how many radians are in a circle. Once again, some nice simplifying happens here when I slam all this together, and I have theta times pi r squared over 2 pi. Those pi's cancel. And this leads to the formula that we had to start with of theta times radius squared over 2. Okay? For area, you need to know that, and you need to know that. Okay? 4 formulas, 2 for arc length, 2 for area, and there's 4 total because the formulas are slightly different if we have radians or degrees. All right, let's use them. Let's calculate some arc length and some area. Number one thing to notice here in the first example, theta's in degrees. Degrees, degrees, degrees. Okay? The formula states theta over 360. Now, if I think about kind of the proportion, okay, I have 1/9 of the circumference. 1/9. That's reducing 40 over 360. Relative to the whole circumference, which would be 2 times pi times the radius, which is 7. Okay? I could throw all of this in my calculator at once if I wanted to. To get that arc length, which is 4.89 centimeters. That's rounded to the nearest hundredth. Okay? Notice I'm switching over to K. Now it's time to look at area, which is still all about the fact that this is 1/9 of the area. So I'm going to take 40 over 360, multiply it by pi times 7 squared. And there I get 17.1 centimeters squared. Be very particular with your units. Arc length is a measure of distance, and it gets single degree units, first degree. Area has 2 dimensions. It gets second degree units, so it should be centimeters squared. All right. Let's take a peek over at number 2. We'll go back to arc length. Okay, so we're looking for this right here, the distance from A to B following that circle. It's in terms of S. This is so the formula we're going to now is arc length in radians, which is theta times radius, 1.8 times 10. Things are pretty straightforward in terms of these formulas when we're in radians. Radians are designed to work well with circle problems because they're really based on the radius of a circle. So there we go. 18 centimeters. Okay. All right, this is theta times our radius squared over 2. Okay, and that's coming from theta r squared over 2. That simplifies to 90 centimeters squared. Okay. Really, the formulas aren't particularly difficult to use. What you have to be careful of is to make sure you pick the right one. That's the most common problem that comes up with these is you got to identify from the problem, are you in radians or degrees, and is it a problem concerned with an arc length or area? Identify the correct formula to use, and if you get to the right one, everything typically works out. What you'll see in your homework as far as slightly different problems from here, it would be conceivable, let's say I gave you that the arc length was 4.89. I gave you the angle, but I wanted you to find the radius. What would change here is S would have been something I had, and R would have been unknown. It's the same formula. It's a matter of identifying the right formula. There's a different unknown. This would lead to a little bit of solving using inverse operations. None of them involve, really, really difficult steps to solve, but that's something your homework assignment will have, is to use these formulas to do more than just plug in numbers and simplify to get s and k. We may work backwards to get the radius or to get the angle theta. So be ready for that. All right, we'll call it quits there. That's everything for 7.2 on arc length and areas of sectors. Make note of any questions, and we'll talk more when we see you in class.